She's a full professor in the Department of Computer Science at the University of Toronto and a co-founder of the Vector Institute for AI. From 2017 to 2021, she was the chief scientist and the head of R&D at Uber ATG. She's a world-leading expert in AI for self-driving cars. Her research interests include machine learning, computer vision, robotics, and remote sensing. Her lab was selected as an NVIDIA NVIDIA lab. She is a recipient of the NSERC EWR Stacey Award, 2 NVIDIA Pioneers of AI Award, a Ministry of Education and Innovation Early Researcher Award, 3 Google Faculty Researcher Awards, an Amazon Faculty Researcher Award, a Connaught New Researcher Award.
You can just stop it. Who cares?
Yeah, and like so many more. Yeah, and I'm very excited, and I'm going to hand it off to her.
Cool, thank you. And I guess the interesting piece is that actually there is new changes of affiliation and things in terms of my life. So let's start actually with that. So apart from being a professor, I am the founder and CEO of Waabi, this incredible new company that you should all be joining. And in particular, before I talk about data sets in the context of self-driving, which is sort of where my passion is, I'm gonna maybe tell you a little bit about what are the underlying things that need to be solved for this task, so that you will understand where the data sets will come into play. So in particular, if you look at the industry, so since the first DARPA challenge in 2004, there has been meaningful progress, right? But if you look at commercial deployment, it's really these super tiny and simple operation domains, right? So there's a lot to be done. And this is due to the fact that, we don't have, or the industry doesn't have autonomy systems that can really handle the long tails of, all the complexity of the real world. And one of the things I'm going to be talking today is that in order to tackle this problem, one of the key pieces is not about having static data sets, it's actually about having real-time simulators that are closed-loop simulators where you can really test perception in action, etc. Okay. And if I guess you want to know maybe two bits about this, as I said, this new company. So we are tackling these two aspects with an AI-first approach that basically is end-to-end trainable and interpretable, that can handle through complex reasoning the long tails, and also we have a breakthrough closed-loop simulator with an unprecedented level of fidelity that allows you to both test the software stack as well as train it at scale. And we are starting with log-haul tracking, which makes a lot of sense because there's a shortage of drivers and it's one of the most dangerous professions in North America. Okay, so I was just talking to some of my colleagues while we were in the panel, and so the other thing that we announced, so this was 10 days ago, is our Series A, one of the biggest in history, where we have amazing investors behind us. So we have offices in San Francisco as well as Toronto. So come and join us if you are excited about solving self-driving and really changing the world through this problem. Cool. So in order to talk about datasets, I also need to explain you how a self-driving car works. So this is my 30 seconds introduction. So basically the vehicle typically senses the environment, then you typically localize with precision of a few centimeters so that you can see, so you can understand before you see the static part of the environment, then you perceive around you, you predict where the different actors are going to be going in the next few seconds, and then basically given this, you plan a safe maneuver. Okay, and then you repeat this every fraction of a second. Cool. So back to the, I guess, the topic of the workshop. So there has been, since, Andreas, Philip, which were my students at the time, and I created Kitty almost 10 years ago to today. There has been a plethora of new data sets. And we started with something that was very perception focused, very camera focused, because that's, we came from computer vision, right? Since then, there has been data sets like looking at prediction. And then, after we created ATG4D, we see that almost every single company has their own data set, and there is challenges at the CVPR and all this stuff going on, right? Now, I think it's important to think about, are those data sets sufficient? This is something else that we need to do. Is this really the right way to go? Right. So I think it's important, like for those of you that are not familiar with this topic, to think about how really autonomy is developed in industry, and you will see the difference. So typically there is data collection. Then something that is super important, as I was mentioning in the panel, is to curate your data so that you have the right data and with high quality annotations. Then you will go through labeling, you create your data set, you train your model, and then basically you estimate your metrics of how well you do. Okay, so this is typically the flow in industry. Cool. So one of the things that is important to talk about is actually the importance of dataset creation. And if you look at this datasets that I was mentioning, there's been very little, thinking about curation, which is really a pity, right? So the way that one can select very interesting and very, great data to basically test, the different software stacks is by looking at the concept of what is interesting. Maybe it's dangerous maneuvers. Maybe it's things that cannot be handled. Right. Also, we need to think about diversity and coverage. Right. We need to be able to cover the entire space of the situations that might happen in the world. And furthermore, what is important as well, and typically done more in industry, is that all of this is basically to improve performance of your software stack. It's not just in the vacuum of evaluating models. Right. So active learning typically is an important component into this process of generating more and more data. Okay. So the data sets are not static, they actually live and continuously evolve. And this is very different from what we observe with these data sets that have been made available for, say, computer vision researchers. Right? The other thing that I would like to mention as well is that if you look at existing data sets, they look at one specific task in isolation. For example, Kitty is a perception data set. I have my data set, in particular my test set, I have trained my model, I'm gonna evaluate in that one task. Right, for some of the prediction data sets like Argoverse, right, I will actually start with some intermediate representations here. I will train my model for motion forecasting and I evaluate my metrics, right? So it's looking at this only one component within the entire system. And this is problematic because typically, particularly perception metrics, do not correlate when your system is good enough with the end task of how well you do at driving. Okay, so as computer vision people, we need other mechanisms to evaluate, our models. On top of this, it's important that we also do things like geosplit into, our training set, our validation set, and our test set should be in different geographic regions. And this is something that we seldom see. There is some data sets out there without naming where they have, over and over and over driving on the same area. That's overfitting in its definition, right? This is not how we're going to understand whether we can drive safely. Also, as I said, these data sets compute these model level metrics for this one specific task. But as the system gets good, right, better and better, then that doesn't really tell us anything. All right, so we need to push towards something different, which is not only evaluation at that component, which is model level metrics, we actually need to go towards system level metrics. So even if you are a perception person, you are in computer vision, right? And then you have a new detector or new segmentation or new something, right? We should be able at the effect that this has in an entire software stack. Can we drive better by using what you're actually developing? Okay, so we need to see data sets where actually the metrics are actually at the end of the system. And this is not something that is out there. Right, so furthermore, if you think about this setup is what we call open loop setup, where basically you have some data you have collected, and then you look at how much you deviate from this, maybe what humans actually did. And that's actually, it's informative, but it's also not super, super informative, because what you would like to test is really how the self-driving car is working with, in action, right? If I make a decision and then I take a decision based on that decision, I'm going to deviate from the human driver. So as a consequence, right, if I just do open loop, I just look at my previous pose is the pose of the ground truth given by the human. I'm not going to look at how basically, if I am out of distribution, if I have compound errors, I'm not going to be able to see any of that. And then when I go and I basically put this in my self-driving car, it's going to do all sorts of crazy things, right? So we need a better way to evaluate. All right, so what do we need for that? So in the industry, the way that this is tackled is by saying, on top of this, what the previous thing is called, what's called log replay or log simulation. On top of this, let's just drive and drive and drive in the world. As academia, you don't have the access, to hundreds of vehicles and hundreds of millions of dollars every year to be able to do this, right? So this is not a solution either, and it's can be pretty unsafe, right? So in order to be able to really be able to tell how well the systems do and how important your algorithm is within self-driving, then we need a closed loop simulator that is able to simulate how the sensors will have observed the scene. And then you need to run this loop in real time so that you can actually do experiments and really understand whether what you're proposing is actually important in the field of self-driving, right? So this will be safe because it's on simulation. You can have safety critical cases, near-like accidents, and it's reactive. So you will really be able to evaluate your entire system. All right, so if you want to do this, then the difficulty comes that we need to create a super high fidelity closed loop simulator. So we need 3 pieces. We need to create the virtual world in a way that is scalable. We need to generate scenarios, and then we need to simulate sensors, right? How the sensors will have observed the scene that is generated by these scenarios, okay? So let's look at some of the ways to exploit things that from computer vision in order to get this at the scale and with super high fidelity. So the first thing that we can do is create these assets automatically by just driving around. What you're seeing here is outputs of a couple of our CVPR 21 papers where just by driving around the world, we can reconstruct every single vehicle you observe super precisely. And also with a single LiDAR sweep and a single image, we can also reconstruct the shape, skeleton, and the skinning weights so that we can animate pedestrians with deformations in arbitrary poses. Okay, so you can use this from computer vision in order to now have a way to create virtual worlds at scale. Then you can generate using some of the prediction models, scenarios as well as behaviors, and basically you can get things like this, where given a map, you are able to simulate these scenarios that are super realistic at scale. Okay, so now we have all the situations that we want to evaluate how our self-driving vehicle is able to drive. And since everything is automatic and we can cover the long tails, as you will see in a second, then basically we can test millions of these scenarios, right? So it's able to do like very realistic behaviors, the way that we simulate. This is an AI system orchestrated everywhere how they behave. Cool. And then we can basically simulate the sensors. And in order to simulate, these scenarios, then again, this importantness of creating interesting scenarios, creating diversity, and creating adversarial scenarios becomes very, very important. So in the next generation of this dynamic data sets that is in a simulator, we need to be able to create things that with high probability are going to make your system fail, right? So this is how we can target the scenarios to discover what your system might not be good at. So these are concepts that are very important, and this is very, very different from how we evaluate systems today. And then basically you can simulate the sensors. This is later. And then you can evaluate the entire software stack. As you see here, we are reacting to somebody coming where the input is basically the sensor data that we generate. And then we can generate this at scale. Right? And then we can create this also for cameras, right? This is another CVPR, I guess 21 paper, where we're going to insert objects here that are fake in logs that were captured before. And the question is, can you say which ones are actually fake? Like, for example, this guy is actually fake. This one too. It's very hard to see, right? So with this level of fidelity, right, we are able to create data so that we can really test, properly perception systems and more. Okay. Cool. So to conclude, so what I wanted to say today is that it's very important that we actually identify interesting data to label, interesting scenarios when we go into a closed loop setting. It's also very important that we understand whether our data sets are complete, whether they are diverse, right? So that for a safety critical system, we need to be able to test everything so that we understand whether we are safe to operate in a particular operation domain. We need to go from model level metrics, as we see on current data sets, to system level metrics, how this component through an entire system will have behaved in the real world. And we need to do it in a way that is reactive, right? So we need to do this with a closed loop simulator with super, super high level of fidelity so that we can really test the entire system. And since, the better the system gets, the more of these scenarios that you will pass. There will be a moment where you do perfectly fine at everything. In order to understand whether there is any underlying other issues, we need to have a way to identify adversarial scenarios and yet create more tests. And again, this is in a dynamic sense where now even the scenarios are going to change given what you're actually proposing. And so hopefully, we will see the field really shifting towards, this closed loop simulation. And we need something more than just Carla, right? We need something that is realistic, that is at the scale. The last bit that I want to make a comment here, which I think is important, particularly for those of you that are actually academics, is that typically academics don't pay attention to licenses. And I caution you for not doing that, because you will be surprised what you're agreeing to when we are actually competing in some benchmarks or downloading a particular industrial player in this domain, okay? Because you might be giving away your IP, you might be giving away your code, you might be giving away many, many things that you don't understand, okay? So be careful with what you do. That will be my last word of caution. And this is all for me today. Thank you.
Thank you so much, Dr. Urtasun. We have a question in the chat that is very linked to what you just said. How important is anonymization and privacy in the self-driving data set? And is this issue being taken into account now?
Yeah, fantastic question. So this has been a problem in terms of sharing data, meaning that in order to share data sets, we need to blur faces and license plates. And when you actually do this, algorithms can actually learn to detect blur, and then that's the way that you detect that certain things are in the scene. So it's interesting the fact that the anonymization might get on the way of progress into solving such an important task. The other thing that is interesting is that for certain sensor configurations, it's even forbidden to record things in certain areas. One example is microphones, right? For example, if you want to have a data set to handle things like sirens and whether it's emergency vehicles, typically you cannot even record raw data. Okay, so this anonymization is a sword of two sides, or whatever is the wording in English, that we just need to be very careful about. The other thing that I think is important when we go to the concept of completeness is also related to bias. And then to make sure that we are able to test in all sectors of the population, in all different geographic locations, regardless of whether this is where the rich population lives, etc. So that's another aspect that we need to be very intentional and careful about. Great question, and I think there is a lot still to be said or to do in this domain.
Okay. Yeah, I don't think we have any other questions right now. So thank you so much for joining us. And yeah, so